Hello, and welcome to A Gross of Physics. Today is day 62, and what we're going to discuss today is impulse. Now, we already defined momentum to be how difficult it is to stop an object, and the equation is P equals mv. The P is a lowercase p, and it's m for mass and v for velocity. So momentum is a vector quantity, which means it has both magnitude and direction. Now, the impulse is slightly different, but it represents how the momentum changes as it interacts with other objects. So in fact, the impulse is just a fancy word for change in momentum. And delta P is the impulse. But since we need a new term or a new variable to represent impulse, we're going to use the letter J to represent impulse. So it's going to be J equals delta P. Now, when Newton talked about his second law, he never actually mentioned F equals ma. Over the years, it's been simplified to be discussed in physics courses because forces are often discussed before momentum. Well, in fact, what Newton talked about was the fact that the change in momentum has to do with the force and the time that force is applied to the object. For example, if I kick a soccer ball and I kick it for 1 second, that's going to change its momentum a certain amount. If I'm in contact with the ball over a longer time period, that's going to give me a bigger change in momentum. So in fact, what Newton did is he wrote delta P equals F delta T as his second law. That does simplify to F equals ma, and I'll show you on the whiteboard in a little while. For now, though, we have this equation that says J equals delta P, which also says F delta T, which because it's changed in momentum can also be written as m delta V. So this is a very scary equation for a lot of students to look at, but it boils down to all of them are equal. So if we have a situation where A equals B equals C equals D, that means A equals D, B equals C, D equals B, etc. So that's what this equation shows. J equals delta P. J is also F delta T. J is also M delta V. Now, some people will take the M delta V and the F delta T and consider that the impulse equation. And a lot of people refer to that as MAV fat. And the reason it's MAV fat is because it's M delta, the delta looks like an A. So it's M delta V, MAV, and then F delta T looks like the word fat. Remember though, it's a delta and not an A. So you don't want to be confused by the fact that it's a delta and not an acceleration. Some students get confused with that and they'll try to find an acceleration to plug in. But either way, if you're forced to solve problems dealing with impulse, what you'll have to do is decide what information you have and what piece of this four-part equation you're going to need to know. Now, more importantly, what it basically says and boils down to is that if I apply a force over a longer time period, I'm going to change the momentum more readily. It's going to be a bigger change, so I'm going to have a bigger impulse. On the other hand, what we might want to do is try to find a way to limit the amount of force on an object. And the way we can do that is by increasing the time of contact. And if you are, let's say, falling off of a monkey bar in the playground, what you're going to want to do when you hit the ground is extend the time it takes for you to stop as much as possible. If you do that, you're going to decrease the force that is exerted on your body. Now, that's one of the reasons why they use pliable materials in playgrounds as opposed to a more rigid material. When I was a kid, concrete was typically on the bottom of playgrounds, gravel, dirt, packed down, things like that. There wasn't a lot of give in them. And what happens is, as you fell off the monkey bars or fell off the slide or whatever you fell off of, you would stop very rapidly. Now, your momentum, your change in momentum was the same no matter what. If you fall from a certain height, you have a certain speed when you hit the ground because of the gravitational pull of the earth. Your mass is constant. And what will happen is your change in momentum will go from that value to 0 when you hit the ground. Well, the longer it takes for you to stop, the bigger the t value, the lower the force, because there's an indirect relationship between the force and the time if the momentum is constant or the change in momentum is constant. So there's two ways to look at this. We could look at trying to increase the time of contact. That's what you do when you play sports with rackets or bats or sticks. You're trying to increase the time of contact. That's why it's important to follow through in baseball. The longer you're in contact with the ball, assuming your force is the same, the bigger the change in momentum. And you have to take a ball that's traveling towards you at a high rate of speed and change its direction and have it go as far in the opposite direction as possible. So not only do you have to slow it down and stop it, you then have to give it enough momentum to travel as far as possible. Same thing with golf. And I understand that in certain situations you don't want to hit the ball as far as you can, but if you're trying to drive it as far as possible, you're going to want to be in contact with the ball as long as you can. So those are instances where you'd want to increase your time of contact. Another example would be playing tennis. If you want to hit the ball at its maximum speed, you're going to want to follow through with your swing and hit the ball as much as possible. If you're trying to just drop the shot, you might want to be in contact for a little bit amount of time so that the ball lands right near the net. Now, it all depends upon the situation, and you're not going to spend your time calculating how fast to hit the ball or what speed, but this is like what you do naturally as you learn the sport. Just like anything else, as you learn a sport, you practice. The same thing applies here in physics. The way we practice is by doing problems. We solve problems, and the more problems we solve, the more adept we become at solving physics problems and doing more complex problems over time. Now, on the other hand, if you want to decrease the force, like the playground example, what you're going to want to do is increase the time of contact. That's why now they're going to use pliable materials like old tires that are shredded, or possibly mulch, or even a rubberized flooring. The same would apply when you're talking about making materials for tracks, for track and field events. The rubberized tracks will allow you to stop over a longer period of time. It has some give to it, so you'll be less likely to injure yourself than if you're playing on or running on a solid track made of, let's say, asphalt or concrete. The big difference when you're talking about sports like football, playing on artificial turf versus natural turf, is how much the ground is able to give when the players hit the ground. The longer you are taking to stop, the lower the force and the less likelihood of injury. Old AstroTurf fields had concrete on the bottom and then a very small layer of artificial grass on top, effectively a little carpet. Now the technology has increased, so even artificial surfaces are more like natural surfaces. So there's less injuries due to hitting the ground. Every time you're running or walking, you are hitting the ground and coming to a stop. So the longer it takes you to do so, the less stress on your body. That's why it's important, if you are doing jumping sports, to have shoes that have enough give in them so that your body can absorb the impact of the ground each time. Sports such as basketball or volleyball, where you play on a hard surface, it's important to constantly bend your knees when you hit the ground and wear soft shoes so that they can give a little more. Once again, the longer it takes for you to stop, the less likelihood of injury because the force decreases. We use the same principle when dealing with airbags in cars and with seatbelts. You want to increase the time that during the collision you stop, and that will decrease the force on the person. Now there are airbags not only in the front where the driver and passenger are, but there are side airbags if you have a side collision. There's also parts of different cars that will give under the strain of an accident, so the car itself crumbles, which gives more time for the entire vehicle to come to rest, thereby saving the passengers from injury. So impulse is important in the way that we want to increase the total change in momentum, or possibly if we want to decrease the total force by increasing the time of contact. Now, that being said, we can calculate the value of different forces depending upon what sport you're dealing with. We can use video footage to determine how long it takes for an object to stop. We can actually watch people hit the ground after a jump and bend their knees, see how far their torso moves, and then calculate the force on their body. So impulse is important, and it's very versatile. So it's going to be a much more useful equation as we move forward. Momentum is important, but using how it changes over time during a collision is going to be even more valuable when we calculate it. So what I'd like to do now is a couple of practice problems dealing with impulse, and we'll see if we can calculate things like the force involved, or merely the impulse, or how long it takes for an object to stop its motion. So let's take out the whiteboard and do some practice problems now. Now we have this term impulse that's going to represent the change in momentum, which is delta p. So we define change in momentum as the impulse, and we use the symbol J. That being said, we have two different versions of the equation. If you have a change in momentum, the mass is going to be the same, but then the velocity is what will change. So we have m delta v. That's a change in momentum. But then Newton pointed out that because of action-reaction pairs, Newton's third law, and F equals ma, and in fact, even because of the law of inertia, we have this other equation. The force that is applied on an object will change the momentum based upon how long that force is applied. So we have this big equation that has four pieces, and any of the pieces are equal to one another. Now, many people, because the ones with the most terms are the last two that I just wrote, we call that mav fat. The deltas kind of look like an A. So we use the symbol delta and we say mav to remember that it's m delta v, and then fat, F-A-T. But one of the mistakes that people make is they'll inadvertently use an A. And this is not the equation. If you put MAV and FAT, then you're going to get it wrong. So just be aware of that. If you want to use mav fat, you're more than welcome. It's just you need to make sure that you avoid using the actual A instead of the delta. Now, as far as Newton goes, what he actually said is he said that delta P equals F delta T. And this is what was written in Principia Mathematica. Delta P then can be rearranged as the following. F equals delta P over delta T. Now if we take this version here and plug it in for delta P, you have m delta V over delta T. Now what is a change in velocity over change in time? Well, it's merely an acceleration. So his F equals ma equation stems from impulses. In order to get something to change its motion, you need to apply a force. The bigger the force that's applied, and the longer that force is applied, the bigger the change in the motion. And the change in motion we call the impulse, which is the change in momentum. That being said, we need to be able to use this equation to solve problems. So let's look at some sample problems next. Here's a problem we can look at. We have a ball that's going to fall off a 2-meter high platform. It's going to hit the ground and stop in 0.25 seconds. Can we find the force? Now, in order to find the force, we have to remember we have J equals F delta T equals M delta V equals delta P. We have our long equation that represents impulse. Now we want to find F. The collision occurs down here at the bottom, which is where we're going to use our time. So we have that value already. We do not have the mass, but hopefully, if we think about it, the mass is going to be a number that let's just assume is 1 kilogram. Let's start with that as part of the problem. Now, if we know the mass, all we have to do is find the change in velocity. Now, how can we find change in velocity? Well, this is an object in free fall. So the givens would be as follows. Vi is 0. D is -2. A is -9.8 meters per second squared. And we're going to look for VF. So, VF squared minus VI squared equals 2AD. VF squared minus 0 equals 2, -9.8, -2. So let's use the calculator. 2 times 9.8 times 2, 39.2. Take the square root, and you have 6.3 negative meters per second. Now that being said, if we want to find the force here, I'm going to look at M delta V equals F delta T. M was 1 kilogram. That was in the problem that I didn't read at first. Change in velocity, that's VF, -6.3 meters per second, minus 0, VI was 0, equals F, 0.25 seconds. So, when we multiply 1 times 6.3, that becomes a negative because of the -6.3, and then divide it by 0.25, you get a force of 25.2 newtons. So the force applied by the ground is 25.2 newtons. Now, negative, because it's going to apply a force opposite the direction of motion. Although the object is moving down, the force is going to be up. So the negative in this case is going to represent the direction opposite its motion. And since the motion was down, the ground doesn't know what's positive and negative. So for our purposes, a negative value of the ground is going upward. So the force is 25.2 newtons. Most problems will ask for the magnitude, which means just the size, not the direction. So you only have to worry about the 25.2. But if the direction is part of the problem, the ground would apply a force upward, opposite its motion. This next problem involves a pitcher throwing the ball at 90 miles per hour. The catcher is going to catch the ball, and the glove is going to move 0.05 meters. And what we're going to try to do is determine the force on the glove. Now, trying to do this, what we need to realize is that the first thing is that this 90 miles per hour needs to be converted. And 1 mile is 1609 meters. 1 hour is 3,600 seconds. So 90 times 1609 divided by 3,600 gets me 40.225 meters per second. Because the miles canceled, the hour, yep, meters per second. All right, now that we know the speed converted from miles per hour to meters per second, what we can do is think about what we're trying to find. Now our equation, J M delta V F delta T. Now the one thing I forgot to mention before, a mass of a baseball is 145 grams, which is 0.145 kilograms. So we know the mass. We know we're going to go from 40.225 to 0 for VF for the speed. So the one variable we're going to need to know is the time. In order to find the time, though, we're going to have to find the acceleration of the glove, because if we know VI is 40.225, VF is 0. The distance it moves is 0.05. What we should be able to do is find A. Then from that, we should be able to find T and then plug it into our equation. So, VF squared minus VI squared equals 2AD. 0 squared minus 40.225 meters per second squared equals 2A.05 meters. So, 40.225 squared divided by 2 divided by 0.05. An acceleration on the ball is going to be a negative 16,180 meters per second squared. Now, the time it's going to take to do this, I would use VF equals VI plus AT. VF is 0. 40.225 plus A, which was negative 16,180 meters per second squared, times T. So T becomes, if I divide the 40.225 by the answer I got before, the time is 0.0025 seconds. Now all I have to do is go back to my original equation and plug in what I know. I know the mass, 0.145 kilograms. My velocity was 40.225 meters per second. F, 0.0025 seconds. So if I do 0.145 times 40.225, then divide that by 0.0025, I can figure out the force on the ball is 2,333 newtons. 2,333 newtons, which is quite a lot of force. And that's why the catchers need to wear such big mitts, because the forces involved with their position are much greater than in any other position on the field. So, that's an example of a momentum problem dealing with baseball and a little bit of kinematics in order to get the numbers that we needed.